Morning, sir. Okay, let's get started. Here we go. Ready to start. Thank you. Okay, lots to do today, so let's get started. So we left off last time talking about volume of a sphere. We're going to spend some time on that example today. So let's talk about accumulation to rate. Back to accumulation. So volume example. So fx equals 4/3 pi x cubed is an accumulation function. Accumulation of volume of a sphere. Okay, accumulation of volume of a sphere. Is that exact or approximate accumulation? Exact. So if it's exact accumulation, how else could we write that? If it's an exact accumulation, we know that we could write it as an integral, right? An integral for some rate of change function, right? Because that's what our integral functions are. They're exact accumulation. So if this is, we're starting with exact accumulation, it must be equal to some integral function for some rate of change. But we just don't know what R is. But that's what we've been in the last week or since exam 2, that's what we've been working on. Starting with that accumulation, figuring out what that rate is. Okay, so let's look at this. And we came up with Can you read that? Is that big enough? Okay, so that was the function we came up with for rate of change based on left x. Okay, so if I start this in motion here, okay, so as x increases, x is our what? Radius of the sphere. Okay, as x increases, what is the black curve? Exact volume, or exact accumulation of volume. And then what is our purple segments? We're approximating that accumulation curve, right? And so in a given interval with h, we get what kind of rate of change in that approximate? Within that interval h, what kind of rate of change is it? Constant rate of change. So in my next step, I'm going to turn on this blue function over here, this R1 function. What will you see when I turn that on? What are you going to see?
Steps. Straight lines.
I heard steps. I hear
All above the
excess. And when you mean straight lines, you mean
horizontal.
Horizontal lines. Steps, right? Oh, that's not the right one. This one. Okay? So within any given interval, we have a constant rate of change. The slope of our approximate accumulation function, right? The slope of the approximate accumulation is a constant rate of change, and that's what this R1 function graphs. Constant rates, a step function. Okay? And so how did we say we were going to get the exact accumulation? Sorry, exact rate of change. So we're going to shrink this value of h, right? So I come along here and I can make h smaller again. Every time I make h smaller, the approximate accumulation gets better, and the step function gets better. And after I make h really small, what's taking shape here? What kind of function is taking shape? Exact what? Rate function. Okay? So when h is very small, we get the exact rate function. Okay, so there it is. But then what we said was what about this alternate version? Instead of being based on left x, we said, what if instead of left x, we just use x? And we get this rate function, f of x plus h minus f of x all over h. Okay, so now what will that be like? So I'm going to turn this on. So I want you to focus on the accumulation side first and try to make sense of what you're seeing here. What are you seeing here in terms of h and x and the approximate rate relative to this approximate rate function? Let me take a minute to talk to the person next to you. What are you seeing here? How does it relate to this new version of the approximate rate function? Go. Okay, so when I turn on, next thing I'll do is turn on this version of the rate function. When I turn on that version of the rate function over there, what are you going to see? What will it be? First of all, it will be approximate or exact rate of change. Still be approximate, right? But what kind of graph will you get? When we use left x, we got a step function. Are we still going to get a step function? What will we get? See, now you get a different constant rate for every x value that you pick now. Remember, within the intervals, that constant rate stayed the same because it was always the constant rate of that segment in that interval. But now for every x value that you pick, you get some different rate of change based on looking ahead h, right? So let's see. So you don't think it's going to be a step function anymore? Will it be a line? Curve? Is it little steps? No, it's not. For every x value you get, so as x increases a little bit, you get a little bit higher rate. But for every x value, you get a different rate of change. And that rate of change, that constant rate of change, shown by the purple segment, is continually getting greater. Is this exact or approximate rate of change? Oh, I heard both. Exact or approximate? It's still based on an interval of h, a constant rate. It's still based on constant rates over an interval h starting at x. So approximate or exact? Approximate. I'll turn the exact back on again. There's the exact. That was the exact we found when we used the left approach. Okay, so this is, that blue one over there to the left is the approximate rate based on this new version with an h of 0.4. How do I make it better? Shrink h, right? So if I shrink h, that version of the approximate rate converges on the exact rate of change. So this is the one we're going to use from here on out. We're going to use this one that's based on continually changing constant approximating rate of change. So let's just look at it again. So for every x, you get a different approximate constant rate for looking forward h, okay? And so that a curve now emerges, but it's still an approximate rate function, which becomes the exact rate function as h gets very, very small. Any questions, comments? Does it make sense? Yeah.
So if you shrink h to the point where it's really, really small,
Right.
Would that mean that you're just pretty much looking at values of x and then taking
No
I don't
values.
know, I don't know. I guess at that point,
Values of rate of change.
okay.
It's still the ratio. It's still that ratio as h gets very, very small, right?
Uh-huh.
That's calculating a constant rate of change, right there. Calculates the constant rate of change, but h is very, very small. So it's like a zillion little constant rates, right?
Okay.
That you're computing each one.
But it's still always x plus h.
Yeah,
Okay.
yeah. Other questions? Yeah.
I know it's like starting at 0.4 for like its age value.
Right.
Why would it be on the y-axis for the exact
Because when x is 0, look, x is 0, there's already a positive rate. Did you see that? When x is 0, we're going from 0 to 0.4, and we're getting an approximate rate, which is, see, watch right at the beginning. You see it starts at some positive rate of change. Well, that's the value of the y-intercept over there, the rate of change. Does that make sense? Okay. So, the question is, what is, so this, again, one more time. The blue, the left, the rate of change function to the left is based on an h of 0.4. If we make that h smaller, it will converge on the true rate function. So the question is, what is this rate of change function? We want exact rate of change. In theory, we understand where we get it, h becomes small, but we want to get a closed form rule for that rate of change function. Okay, how do we do that? We did this last time. So if f of x plus h minus f of x over h is the rate of change, what is f of x? 4/3 pi x cubed. That's our accumulation function. So if that's true, then what is this when f is 4/3 pi x cubed? Don't look at your notes from last time. Just do it again. Don't look at your notes from last time. Do it again. What is the rate function, the approximate rate function, when f is 4/3 pi x cubed? Practice. Okay. So we just look at f of x plus h. What's the input? For f of x plus h, what's the input? X plus h. So this function says cube the input, multiply the result by 4/3 pi. So what is f of x plus h? Yep, so it's going to be x plus h cubed, cube the input, and multiply by 4/3 pi. That is just f of x plus h. What is f of x? So now we're doing this part right here. What's the input? X. Well, when the input is x, we know it's right there. We cube the input, multiply by 4/3 pi. 4/3 pi x cubed. All over h. Did I miss something? So simplifying this for a very, very, very small h gets us the exact rate of change function. That's the point. Now we want to do some algebra to simplify this, and it'll give us this exact rate of change function in closed form. Okay, in closed form, meaning we can just give it lots of input values, and it just will give us rates of change, rapid fire, right? Rapid fire. So let me show you how graphing calculator can actually help us do this, but only because we're already experts at algebra that we can use it. Okay, so is this what we just came up with?
Yeah.
So watch, I can grab onto that x plus h cubed right there, and I can say math, expand.
That's magic. Can you do it again?
So here's the thing. You're seeing visuals about accumulation and rate that maybe no other students in the country are seeing. How when you make the changes small, you get the accumulation function emerges and the rate function emerges. And you all sit there and okay. But then I show you how it does algebra. You get excited. Okay. All right. I'm trying to change that. Okay. Okay, so here again, we got 4/3 pi times that whole thing. And I think it's simplify that. No, that's not what I wanted. Undo that. Let's see. Is it expand again? Yeah, there we go. Okay, so then I just multiplied the 4/3 pi into all the terms. Okay, copy, paste. And so now for that numerator, can you see what's going to happen in the numerator? There's a 4 pi x cubed over 3, and then minus 4/3 pi x cubed at the end. So if we simplify that, if you go math, simplify. We've got to get this 3 to be on all of them. Calculate? No. It doesn't like the 4/3 pi. Let's see. This fraction is messing it up. So let's, what can we do? No. So we'll just grab what we want here. So we're just going to, we know that will go away with this. There we go. So the 4 pi x cubed over 3 minus 4 pi x cubed over 3 results in this right here. Okay? And now we'll simplify that. And we can factor out an h. Does it factor? I think it factors, right? Somewhere?
Isolate.
Maybe? No. I didn't practice this before class, sorry. All right, but anyway, so we know, so now look, there's an h. there's an h in all three terms on the top now. So once you subtract out that first term and that last term, the remaining terms all have an h. And so we can factor that out. So now there's no h's in the first, and there's only one h in the second, and there's two h's left here, and then that should simplify. H goes away, and we have this. So we want h to be very, very small, and our problem is when h is in the denominator, h becoming very, very small is like making h so small that it's like 0. So when we get that h out of the denominator, now we can go ahead and say, what will this be when h gets very, very small? Right, so as this will go away, and this will go away, and we have it. 12 pi x squared over 3 equals okay, and this was, we called this R2. Okay, so this is the exact rate of change function because that 4x squared is the same as that original expression, f of x plus h minus f of x over h, when h is very, 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 very small. Or as h, the limit as h approaches 0. The limit as h approaches 0. Okay, so let's go back to the graph. So now we know what this function is. For very small h, R2x is 4 pi x squared. All right, so come right here. When x is 0.8, what's the y value of this point right here? So this point is 0.8 and what is it? So how would you find the exact value of the rate of change at 0.8? We can just stick it right in there, and we get 4 pi 0.8 squared, 8.042. Okay, so what does that number mean? What does that number mean? It's maybe the most important question of the course. Okay, it is that's what it is. And what is the number 8.042? What is the significance of that number 8? See if you can talk it out with the person next to you. What does that number mean? 8.042. Go. Okay. Anybody want to give it a try? What are we talking about now? Again, this question is maybe the most important question of the whole semester. Do you know what that number is, what it means, what that value means? Anyone want to give it a shot? Talked a lot about it. Michelle?
0.8, 8.042 is how many times 0.8 is changing. Like it's changing 8.042 times with respect to 0.
Okay, and what quantity is the 0.8? So you're on the right track. What quantity is that? The input is what in this function? Radius. So maybe centimeters. Who knows? We didn't specify a unit. It's the radius of the sphere. So you're saying when the radius is 0.8. What's that?
So when the radius is 0.8, volume will be increasing at 8.44 times with respect to x.
He said when the radius is 0.8, the volume of the sphere is increasing 8.042 times as fast as the radius is changing. What do you think? Are we under attack? What's going on? Okay. Hopefully that will become white noise and will go away. All right, so this is the rate of change. Okay? So we talked about if we increase the radius a little bit, if we increase the radius a little bit, then what would we expect? So the radius is currently 0.8. If we increase the radius a little bit, what do we expect? What's that? No, I want to interpret this number 8.042. What does it tell us if we increase that radius a little bit? What's that?
Volume will be 8.042 times greater than the respective change radius.
The volume will be 8 times as much as the radius. Yes or no? If x increases a little bit, then the volume will be 8 times as much as the radius. So you want to revise?
That's what I meant to say.
What, I don't know what you meant to say. So tell me.
Okay, so what I meant to say is like for every change in the radius,
Okay.
the change in volume will be 8 times greater.
Okay, that's different. So he now said for a change in the radius, the change in volume will be 8 times as much as that change in the radius. What do you think? What's that? Okay, only at that radius. Only at that radius. So what about if the radius changed, say, 0.5 from here? So that would go up to 1.3. So here's my change in a change of radius of 0.5. Will the volume increase 8 times as much as that?
No.
Why not? Right, because the rate is doing what? The rate is continually changing. So, it's true that the changes in volume are 8 times as much as the changes in radius if what? We have to have a condition now.
If the radius is 0.8.
If the radius is 0.8 within like 0.01.
So it's about our the change in radius that we're talking about. If I do a change in radius of half of a unit, by the time we get a half unit away, the rate has changed a lot. Okay? So instead, that's true that the change in volume is 8 times the change in radius if, what's the key factor here? What's that? If that change in radius is very, very small. If that change in radius is very, very small. So if I come here and I Try to just ignore that. I'm going to zoom in. So now I'm talking about very, very small changes in radius around 0.8, a radius of 0.8. So for very, very small change in radius, here, now we can say the change in volume is, I wrote, so 8.042 times as much as the change in.
How small do those changes have to be?
Well, so you could, for different size changes, you could figure out how much the error is, right? So there's no set amount, right? So how about a change of 0.1? What will the change in volume be? How would you find it? How much will the volume change? When the radius is 0.8 and I increase the radius by 0.01, how much will the volume change? Or what would we predict? 8 times 0.01, or about 0.08. 0.08 is how much that volume changes. I think 0.42, something like that. So this everything about constant rate of change still applies, but just for very, very small changes in x. So it's still all the principles of constant rate is the meaning of the output of the rate function for very, very small changes in x. Okay. So let's go back to this. So now we've got that rate function, right? So we said we've got accumulation function. It means that it's the accumulation. That means it's an integral for some rate. We don't know what r is, but we just found it. The rate function we found was 4 pi x squared. So therefore, our accumulation function can be written as the integral from 0 to x of 4 pi t squared dt. That's back from exam 2. So when we found, here's the deal, when we found that rate function, for that exact rate function, for the exact accumulation function, we didn't just find out that. We also found out what the exact accumulation function was for this open form expression. So remember before we said we have open form accumulation functions, but we don't know what the closed form is. Well, for this one now we know what the closed form is. So when we found that rate of change, we also learned something else. We learned what the accumulation is if you have that rate of change. So if we started with this question before, we had to put this here in graphing calculator and graph it for us or calculate values. But now we have a closed form of that integral. And it's this accumulation, 4/3 pi x cubed. So every time you get a closed form rate function from an accumulation function, you just learned two things. You also just got a closed form accumulation function from a rate function. Does it make sense? No? So I'll try one more time. We just acquired this closed form rate from this accumulation function. Well, that means that if you had this rate of change function and you expressed it as an open form accumulation, well, now we know what the closed form accumulation is. It's the accumulation function we started with. Okay, so let's talk about notation. So f is any function. We're going to use this function, r f of x, to mean f's rate of change function, the function whose values gives the rate of change of f with respect to x. That is this one. So this is going to be our rate of change function that we use. We're not going to use left x anymore. So at the beginning of class, we saw the difference, right? This does not give a step function. It gives a continuous function, but it's still approximate if h is not small. It's still approximate if h is not small, but it gives a continuous function, not a step function. So how do you read it? It's the rate of change of the function f with respect to its input x. So we're going to practice saying that, okay? the rate of change of the function f with respect to its input x. Okay, so let's find our f of x if f of x is 3x squared. Practice. So at this point, all we know is one thing about what the rate of change of f with respect to x is. Everyone should be able to write it down. So what is the rate of change of f with respect to x? We only know it as one thing now. I hope you're all saying this. Okay, is it exact or approximate? Oh, they're fighting.
Depends on what the size of h is.
Say it louder. He got it. Hold on, he got it.
It depends on what the size of
It
h is.
depends on what the size of h is.
Yeah.
It's both. It's both. It could be either. So we can just use this generically. We know that if h is small enough, if h is, we look at h approaching 0, the limit as h approaches 0, then it's exact. So for us, it can mean either. It can mean either, just we have to know what h is. All right, so what is f of x plus h? Let's do it fast here. So this says take the input squared and multiply by 3. It's going to be 3 times input squared minus okay, then we can multiply this out. X plus h squared equals okay, rumbles in the crowd. Is there a question or what's up? Friday. Okay. Keep going. What's next? Multiply the 3 through, which allows us to do what? Positive 3x squared minus 3x squared. Some of you have been waiting all semester for problems like these. You love it. Move those symbols. Okay, so 3x squared minus 3x squared. H, we'll factor out first. Six x plus 3h. Is it accumulation or rate of change? Is it exact or approximate? Depends on h. Depends on h. If h is relatively big, then it's approximate. As h gets small, then we get 6x. Okay, we just learned 2 different things by doing this problem. Tell the person next to you, what 2 things did you learn by doing this problem? Go. Okay. What was the first and obvious thing that we learned? What was the first and obvious thing that we learned? Which is what? So we learned what that is. What is that? If you have an accumulation function that's 3x squared, we learned that the exact rate of change is 6x. Then that tells us something else. What's the other thing that it tells us?
It gives us the exact rate, or it gives us the exact accumulation.
If we had this accumulation function,
Yeah.
if we had this open form accumulation function, now we know what? The closed form, which is 3x squared.
So it's open form, it's closed form accumulation.
What's that?
Is it open form accumulation?
So by being able to find closed form rate functions, it allows us to start finding closed form accumulation functions, which we couldn't do before. Right. Before we had open form accumulation functions based on a given rate. But now that we can find closed form rate from accumulation, that means that we can start knowing what some closed form accumulation functions are. Does it make sense? Okay, so two forms of the same accumulation function. The integral of the rate dt and 3x squared. So they're both exact forms of accumulation. That one's the open form. It reflects the process, summing up a bunch of little bits of change when the rate of change is 6t. And then the closed form, which is a standard function. It's like a fast track to results. Plug in an x, it spits out a y. So you plug in an x, it spits out the accumulation. Plug in another x, spits out the accumulation. That one doesn't do that as easily, right? But it shows the process, the open form. Okay, so this is open and closed form accumulation. They give the same value. They give the same value. Okay, what about rate of change? Rate of change. The one on the left is? Which one is exact? Both are exact. Because we're taking the limit as h goes to 0, that makes our R of f function exact. Which form reflects process? Left or right? Left, and it's called open form. Closed form. They both give this, they're both exact rate of change. So they both give the same value. Any questions? Okay, so now we're going to, we did x squared, the square example. We did the volume example. We just did 3x squared. So now what about just any function x to the n? Any function x to the n. So let's show what's going on here. So don't try to write this all down. Try to absorb as much as you can. Take notes later from the video. So remember that x plus h squared has 3 terms. X plus h cubed has 4 terms. And so on. Okay? So x plus h to the n has, in terms of that, n minus 1 terms. A lot of terms, okay? A lot of terms. Does it have, yeah, it has n plus 1 terms. N plus 1 terms it has, okay? So, and this would be the generic form of the expansion, so, and so on. So what happens? The powers of x go down by 1, all the way to x to the 0, while simultaneously the powers of h go up. So here's h to the 0. Powers of h go up 1, 2, until they reach n. Okay? And so powers of x go down while powers of h go up to get all the terms. Okay, so we know our R of f of x, that's our rate function. And so then f of x plus h is x plus h to the n minus x to the n over h. And so now we're going to expand, like we saw on the last screen, we're going to expand that x plus h to the n. There it is. Okay, but the same thing's going to happen that happened before. So this is a little ugly, but the same thing's going to happen before. What do you see about every single one of these terms except the first one? We got x to the n and minus x to the n, and all the rest of the terms have an h. So it's the same thing. So those go. And all the rest of the terms have an h, so we can. So what just happened here? So what happened here was we split up, took all this over h and this first term over h. So when we took that first term over h, the h's go away and you're left with this thing right here. Okay? And then the second through the rest of the terms is now this thing right here. So this right here is this right here. Those are the same. And when you combine the h with that first term, you're left with this n times x, n minus 1. So what's the deal? All these have an h. That's the point. All these here have an h. This one doesn't. So the first one ends up without an h, and all these have an h. So when h gets very, very small, we get this. What is it? Is it approximate or exact rate of change or accumulation? Approximate or exact rate of change or accumulation? Exact rate of change for what accumulation function? X to the n. For this accumulation function, okay. Ready to let me finish? Okay. For this is the accumulation, for this accumulation function, this algebraic process shows that this is the exact rate function for that accumulation function. And there, that's summarized right there. So, exact accumulation, exact corresponding exact rate. Okay? So, if f of x was x to the 18th, what does this general rule now say that our exact rate function is? So the power is 18, that becomes this coefficient. And the new power for the rate of change is 1 less than what it was before. So this is the rate of change function for x to the 18th.